things like that, you create three-dimensional objects, things that have volume. Well, things that have nice round volume, just like that. Okay, what would happen if instead of revolving these two-dimensional objects, we change it to just one dimension? If we just revolve a single plane line like this, you wouldn't get something that has volume, but you would get something that has area. So that is the question. If you revolve it, you'd get something like this. And so this is sort of the outside of a cylinder. And the question is, how much area do we have here? Area all the way around here. That's the question. For shapes like this, it's quite simple. You don't need much. What you do is you imagine yourself cutting it here. If you cut it, you open it up. Really, what looks like a ring or a cylinder can be made to look like a rectangle. And so the area would be equal to the base times the height. Base times height. It would be the same thing over here, except the base is sort of curved. It's got a little twist to it, so the base would be equal to 2 pi r if you were to wrap it around. We've done this type of argument before. And so we conclude here that if this is a radius r, then the surface area for this guy would be equal to 2. If this is r, the surface area would be 2 pi r times the height. Again, this would be the same thing, same base times height. How do we all cut it here? You cut it there with some scissors, and really you make it look like a rectangle so that you can see the area is just base times height. Alright, that's it. That's your dose of common sense. No, you get more common sense today. Today you get a double dose. You ask, what if it wasn't a nice shape that's just an upright rectangle? What if it's slanted like this? What would we do then? Well, we would do a similar thing here. We would still, figure out this length S. We would call that S, and then we would cut it this way. Cut it this way, this way, this way, this way, this way, so that the cuts look like this. And of course, we would do the same thing that we did when we did Papa's theorem. We would turn these around so that we can see that as a rectangle. Again, it would be the height of this, which would be S, and this would be 2 pi r. The only question is which r. You have a small r here and you have a big R here, and the answer is, well, it's neither one of those. We would use, of course, the middle radius, something in the middle, the average radius, and so and that line right there would be the same as, it would be going right through the middle, through these ones right here. So the r that we use is the radius, the middle one. Okay, and so we get this classical formula. This shape is called a frustum. A famous surface area for the outside is 2 pi r. That's the length using the middle radius, using this radius. 2 pi r times the length. This is how tall the rectangle would stand if once you've cut it up and positioned it in the right place. Okay, and now that's it. That's all the common sense you get. That's all you need. The rest of it is taken care of by the fundamental theorem of calculus. Let's do something that's not so classic here. Something a little off the beaten path. What's a typical example, but it's not something you might have seen before. So this curve, let's say it's a y is equal to x square curve, and we take and we say we spin it around this way. If you spin it that way, it would create, see, if you have trouble spinning, what you should do is just spin one point at a time. Spin this point, put it over here, spin this point, put it over here, and then just make circles that join them. So it would look like this. Wow, sometimes my circles come out too straight. Sometimes they come out too perfect. What will it be today? Perfect. Perfect. There you go, I'm getting the hang of it. So that's what you would get if you started spinning those points around. You get like a bowl, and the question is, can we find the surface area? And the answer is an affirmative. Hell yeah, we can find it. And how? Well, it's so easy. We've dominated the jewel of the 17th century. The jewel of the 17th century. Let me clone this so we can see how we dominate the jewel of the 17th century. Let me take everything that we don't need so we can just, whoops. What a beginner. Sorry. Alright, so here we go. I take this piece right here and I spin it around, and here's what happens when I spin it around. I would get another piece just like it on the other side, and then these pieces I could join with little ellipses. Perfectly round ellipses. Perfectly round ellipses. There you go. And this would be the area that I'm trying to find. And let me think. So I set out to find that little area. And that little area would be given by 2 pi r toward the middle times the length. The length here would be really small, and it's shaped this way. So the obvious thing would be a ds. That's how long it is, ds. The radius would be from here to here. That would be the radius. The radius to the middle. This is so thin that you don't even have to take the average of the x's. Remember, this is an infinitely small, the differential frustum, an incredibly small shape. So you could just call this x value. I'll call this one x1. Call it x1. I'll call this one. I'll call this one x2. And so then this is the radius from here to here. That becomes 2 pi x1 minus x2 times a ds, which would be the usual dx square plus a dy square. And that's your little area for little frustum. Now, you decide whether you're going to keep the dx's or keep the dy's. You get to keep one of them, so you can differentiate with respect to x or with respect to y. Let's just assume we keep the x's. There's nothing special about them. You could do it with the y's, but let's just choose the x's. That means I want to get rid of the y, and I want to get rid of everything that's not a constant or an x. So I go through this x1, I keep the x's, and it's not a constant, so this one right here is changing, so I keep it as x. x2 is a constant, so I exchange it for the constant. x2 is 0. The square root of dx squared dy squared. Well, wait a minute, where am I going to get that? That would be from the relationship between x and y. So from that relationship I get, let me do this here off on the side here, I get that dy is equal to 2x dx. Perfect. That would mean that my dA is equal to, well, that would mean that my dy from here, dy squared would be 4x squared dx squared, right? Making my dA would be 2 pi x square root of dx squared plus 4x squared dx squared. Both have a dx squared. I'm going to pull that one out, so I get 2 pi x square root of 1 plus 4x squared. Dx comes outside. And now I do the magical stuff, my favorite part, the fundamental theorem of calculus. I add up all these little frustums. I have a whole bunch of them creating the entire surface area. And I look at the x, the differential is x, so I'm going from f for x's. I forgot to set the values at the beginning. Let's just go from 0 to 2. Okay, so my x's, I got a whole bunch of these frustrums, a whole bunch of them, and they start from 0 and they go all the way to 2. So we go from 0 to 2, and the rest of that is pretty boring. But we probably need to practice, so I should do it. Let me do it, why not? So this one I would do using a u sub. I'm going to make my u is equal to 1 plus 4x squared. That would make du equal to 8x dx. That would make my integral 2 pi 2 pi x, I'll leave the x in there, square root of u dx. That would be 8 over careful. Okay, so my x dx is equal to 8 du over 8. So my dx would be du divided by 8x. And that's kind of nice because look at how nice this x cancels that x. And you get that in u, this integral looks like 2 pi times the integral of u to the 1/2 times du. I could take that 8 outside. How do you like them apples? Now it's really dangerous. It's really tempting here to put the limits that I had before. I had 2 to 0. Might be tempting to put these limits 2 to 0, but it's really wrong. These limits were for x. We said that x goes from 0 to 2. If you want to put limits here, you either got to finish it and convert back to x's and use x limits, or convert the limits to u so you can use u limits. I'm going to do the latter. So I'm going to convert to u limits. When x is 2, I plug it into my dictionary. When x is 2, that becomes 2 times 2. It's 4 times 4 is 16, times 1 is 17, or plus 1 is 17. And when x is 0, u is 1. So this becomes 2 pi over 8 u to the 3/2 times 2/3, going from 17 to 1. And then you would plug in the 17 and plug in the 1 and subtract it. And that's it. Racket. Our first non-trivial area. Very nice, huh? Let's go back and retrace our steps. What was the deal? What did we do here? It was all about just slicing it up into small little pieces, make frustrums out of it. Use this fundamental idea for the area of a frustrum. It's not fancy. You can derive it yourself just by looking at a frustrum and looking at this picture. If you can see this picture here, you can figure out that the area is equal to 2 pi r times the length of s. Of course, the r has got to be the one to the middle. Okay. This has the same sort of flavor, by the way, as the Papa's theorem that we did last time. It's not an accident. It's the same idea. All right, that was a not so classic one. Let's do a classic one, like the surface area of a cone. If I take this triangle here, I make this size A and this size B and this size C, and I spin it around, of course what I would get would be a cone, right? I'll get something like this. Circles, nice circles, beautiful. Nice circles, beautiful. So I get a cone, and then the question is whether or not you can find the lateral area, the outer area for that. It's easy. We could do it, well, we could just do it by looking at it as a special frustrum where the inner radius is 0. But let me just let that slide. Let's practice our frustrum skills. So we cut this up into infinite many little pieces that are infinitely small, and they would each look like tiny little baby frustrums, just like this one. That right there, that's a frustrum. And the challenge, probably the biggest challenge, would be to find the little area for the frustrum. If I can do that, the rest of it will be a piece of cake. So that little surface area would be, again, 2 pi r to the middle times the length. In this case, this is how long the frustrum is, so it's a little ds. That would make it dA is equal to 2 pi r. This is the distance r from here to here. It's just x. I'll call this x1. I'll call this x2. So it's x1 minus x2. My ds would be dx squared plus a dy squared. I would make a decision here whether I'm going to go with x's or y's. I'm going to go with x's. So I keep that x, I exchange that one because it's a constant. I keep these ones, and I want to exchange the y's. How do we exchange the y's? Well, the y is related to the x by whatever point this is, and that would be determined by equation for this line right here. This line right here will determine how x and y are related. So I need to find that equation. We think y is equal to mx plus b, right? And that is so high school. But I can do it. I think I still remember high school. The y-intercept would be b. That's funny. It's actually the same b. And the slope would be rise over run. So you rise down b over a. So your y would be equal to negative b over a. That's the rise over the run. So there you go. That I need my dy. dy would be negative b over a dx, and this would go. So I need a dy square actually. I would put that here. So if I square this and I square that, that's what goes over here. So I'd get b squared over a squared dx squared. Okay? As easy as it sounds, that's all you got to do. and we give ourselves a little bit more room to grow. So then our differential of a would be equal to 2 pi x square root of dx squared plus b squared over a squared dx squared. So our little differential of x would be 2 pi x. Got the dx and the dx squared there I could pull out, so it'll be 1 plus b squared over a squared dx. And I think I cleaned that up, right? I need to extend this page though. Easy, Bella. So dA would be equal to 2 pi x square root of a squared plus b squared all over a squared dx. And that would be dA is equal to 2 pi x a squared plus b squared. Keep in mind that this was a right triangle where this is a squared and this is b squared. So a squared plus b squared is equal to c squared using the Pythagorean theorem. So I can exchange this for c squared over a squared dx, which would clean up nicely. This would be 2 pi x times c over a times dx. And then I do my magic here. My favorite part, slap a sum on both sides, observe the differential. It's with respect to x's, so my x's are going from 0 to a. And wait, there's more. And that would turn into, let me see, everything that's a constant can come out of there. Come out and play over here. And that would simply leave x dx there from 0 to a, which would turn into 2 pi over ac times x squared over 2, going from a to 0, which would of course turn into 2 pi over ac times a squared over 2 minus 0 squared over 2, which would of course be, this goes away, so you can forget about that. It's a 0. One of the a's goes away, the 2 goes away with that 2. This is cleaned up really nicely. One of the a's goes, so I'm looking at pi c a. That's it, that's the area. If you take a whoa, I can make them straighter than that. Watch this. Straight. Come on now. Straight. If I make if I have a triangle like this, where this is A, B, C, and I spin it around this way, creating a cone this way. Yeah, I've been practicing my circles. The surface area for that cone will be given exactly by pi ca. It's timeless. Told you. It's all by cutting it up into little bitty tiny frustrums. Of course, it's silly because we could have done this even in junior high. Even if you were like in 3rd grade, we could have done that just using Papa's ideas. Watch this. I'll do it using the ideas of Papa's. Papa's would say, forget about all that calculus stuff. That doesn't even exist. The world was not even pregnant with the ideas of calculus when Papa's discovered this stuff. So Papa's would have said, you know what? Just take the average. If this is A, find the middle point. Center of mass, if you will. That would be A over 2. This whole thing is A, so this thing is A over 2. And just focus the whole thing. The whole thing is C. Focus all of its might and all of its length on the midpoint, and then rotate that. So it would be 2 pi r times the length of C, where r is going to the middle. So it would be 2 pi. What's the length? What's the radius to the middle? It would be A over 2 times C. That's the length of the curve. So it would be 2. These twos would cancel, and so you'd get that pi AC. Using the ideas of Papa's. Instead of, because this has a small little tiny radius of 0 and a big tiny radius of A, Papa's would say use the average. Use the average, the center of mass, A over 2, and you just rotate the whole thing about A over 2. And you get a same result a different way. The richness in this class is amazing. I'm starting to like it. Alright, you want to do some more timeless things? Let's do one more. How about take a little portion of the circle here and let's just spin it around this way, and you can imagine what you would get. You would get something like this, and you'd get you know what happens if you spin it this way. You get things like this. Of course, that's a sphere, right? That's the ugliest sphere I've seen. Alright, that's a little better. So you'd get a sphere, and so the challenge is, can we find can we derive the volume of this, or the surface area of a sphere? Probably you already know it. If you went through high school, you know that the surface area is what is it, 4 pi r square, right? So everybody knows it. If this is r, the surface area is 4 pi r square. Question is, can we derive that a different way using little tiny frustrums? And the answer is, again, of course we can. All we do is take little tiny frustrums like this and spin them around, one little frustrum at a time, just like that. Okay. If we can find one little area for that little frustrum, it'll be so easy. We'll just add them all up. We'll add it up infinite many of them, and then we'll be in business. But I gotta go take my daughter to ballet class, so I'm gonna put this on pause. I'll come back later, okay? Don't forget her ballet class. It's more important. Let me finish it real quickly. So the little area, let me think. The area would be 2 pi r to the middle times the length, which would be a ds. So the little area would be equal to 2 pi, this would be x, I call this x1, I call this x2. So it would be x1 minus x2, right minus left. The ds would be, as usual, dx squared plus dy squared. That would make dA is equal to 2 pi x times the square root of dx squared plus dy squared. Alright, I gotta make a decision here. I'll keep the x's or keep the y's. I'm gonna keep the x's, so I gotta get rid of the y's. I need the relationship that that's between x's and y's for this one right here. So that's given by x squared plus y squared is equal to r squared. So therefore 2x, I'm gonna slap a d on both sides. D on that side, a d on that side. So I get that 2x dx plus 2y dy is equal to 0. The r is a constant. And that gives me that, let me think, that gives me that 2x dx is equal to negative 2y dy. That gives me that dy is equal, cancel the 2's, I get a negative x dx all over y. So therefore dy squared is equal to x squared over y squared dx squared. But wait, there's more. I got to get rid of those x's anyways. So the y squared over here we said was equal to r squared minus x squared, so I can substitute that in here. So my dy squared is equal to x squared all over r squared minus x squared dx squared. And now it's looking perfect. I take this guy and I substitute it way up there, right there. And that will give me that the dA was equal to the dA is equal to 2 pi x square root of dx squared plus x squared all over r squared minus x squared dx squared. What's up, ballet girl? Where are you going?
Mama, you're supposed to take me?
The teacher called me. They said they canceled ballet today. I'm just kidding. No! So, where were we? We were trying to simplify the small differential area for the outer surface area of the sphere. Let me think. This is where we left off. So this was dA is 2 pi x. I'm going to clean this part here. I want the same denominator, so I'm going to go with r squared minus x squared all over r squared minus x squared plus x squared all over r squared minus x squared dx. So here I just changed the one here. That one became this part right here. And it's just algebra here. I'm not really doing anything that interesting, except for those little blue letters that will disappear. See that? 2 pi x, that would be, let me think, on the numerator, the x squares and the negative x squares go, so you just get r square all over r square minus x square, and all that with the dx on the outside. That will give us a dx on the outside. Let me think, r is a constant, so I can pull that r out, treat it like a constant, like the constant it is, 2 pi r, and then I just have x over the square root of r square minus x square dx. And this x is the one up here and up here. The r, which the square root of r square became r, we're assuming it's positive, came over here. And it's clean enough for us to do what we got to do. We need to integrate this. And we need to integrate the differential is x, so let's observe. What this is going to give us is just half the surface area of the sphere. But that would be good enough because we just multiply by 2 and calculate the compute the whole thing. My x's are varying from, look at my little differentials. I can start counting here at 0 and I go all the way to the radius r. Again, r is a constant, and so that would be good enough from 0 to r. And let's see what that gives us. Of course, it's an expected result because we should all know the formula for a surface area of a sphere, but it's still nice to be able to derive it. We're going to be able to see it right now before our eyes. Alright, so we got to do this integral. I'm leaning towards a u sub on it. A u sub would look something like this. I would make u, trig sub would also work, but u sub will as well. So du, remember r is a constant, so it goes negative 2x dx, and so the x dx part, that's the x dx part, that's what I'm going to substitute, and I'll substitute a half of du on there. And talk is cheap, so I'm going to do it. This would be the integral from, this would be du with a negative 2 out here, du. There I go, substituting the du divided by the negative 2. On the numerator, on the bottom, I'll have u to the 1/2. Again, it's tempting to put these limits 0 to r, but it's actually kind of a bad idea because these are x limits, and so you wouldn't want to put them on a u integral. Alright, so I continue with my calculation here. This is a basic one. This is pi r integral of u to the negative 1/2 du. And I write it this way because it's really easy to do the power rule when it's written that way. U to the negative 1/2 du. I just wrote it again so you guys will get it. Or have a better chance of getting it. I'm just kidding. Negative pi r. Alright, so the you add 1 to the exponent, so that becomes 1/2, and then you divide by the new exponent. Dividing by half is the same thing as multiplying by 2. And then I change back to my x's. So I go back to the dictionary. My u's were how much were my u's worth? They were each worth r square minus x square. And of course this whole thing is to the 1/2, and it's going from 0 to r. That will give us, let me think, I plug in, I'm going to keep this thing out of it, negative pi r times 2. I'll keep that out of it because it has no x's, so it doesn't care what happens with x. Whoa. Whoa. Alright. So I plug in r, that gives me 0, because r squared minus r squared would be 0, actually 0 to the 1/2. I plug in 0 here for x, and that would give me r squared minus 0 to the 1/2, that would just give me r. And that cleans up into negative and a negative. I see a negative, negative, that gives me positive, so it would be 2 pi r squared. What we just calculated was the surface area for the top part of the sphere. The surface area is 2 pi r. Of course, the bottom would be another 2 pi r for a grand total of the grand total for the entire sphere would be, see, I've been practicing my circles. How do you like them circles? The grand total would of course be 4 pi r squared, double the previous calculation, an expected result. Nice, huh? Classical stuff. Deriving the recipe for the surface area of a sphere. It's well known. You probably heard this in junior high or elementary school. Surface area for a sphere is 4 pi r squared. You can own it now. It's yours, thanks to the grand idea of cutting things up into small pieces. Alright, that was really, really nice. I think we shall stop there and let you guys work on the homework and the self-quiz.